This is Pre-Calculus Section 1.7 Day 2 Notes. We're going to continue talking about solving inequalities, but today we're going to introduce inequalities with quotients. So if you look at our first example, we have on the left-hand side 8 plus x over 1 minus x, and that's greater than or equal to 2. So our first step here has to be to move all terms to one side of the inequality because we need a 0 on the right-hand side. So I'm going to subtract that 2 over. So that's going to make our inequality look like this. 8 plus x over 1 minus x minus 2 is greater than or equal to 0. Now the problem is we can't proceed with the problem until we create one fraction on the left side of the inequality. So now I have to do some addition and subtraction rational expression work. Right now I have a denominator of 1 minus x in my first fraction, and I have a denominator of 1 in my second fraction. So it makes sense that my common denominator should be 1 minus x for both fractions. Okay, and I'm going to try to add these two fractions together. So when I look at my first fraction, I didn't change the denominator, so my numerator is going to stay 8 plus x. In the second fraction, I changed my denominator to 1 minus x, so I'm going to have to take that negative 2 and multiply it by 1 minus x. And of course, this is still all going to be greater than or equal to 0. So now I'm going to go ahead and I'm going to do the distributive property right here. And I'm going to combine everything over my common denominator. So I'm still going to have 8 plus x, but then I'm going to have negative 2 times 1, and then negative 2 times negative x is going to give me positive 2x. And this is still greater than or equal to 0. And when I combine like terms, I end up with 2x plus 1x, that's going to be 3x. 8 plus negative 2 is 6 over 1 minus x, greater than or equal to 0. And then finally, one more thing I can do is I can factor a GCF out of my numerator. So I could take out a 3, and then I will have x plus 2 over 1 minus x, which is greater than or equal to 0. Okay, whew, there was a lot of work. All right, so now step 3 is going to be to determine the values that make the numerator equal to 0. Okay, well, the values that make my numerator equal to 0, or the value, is going to be x equals negative 2. And since we're trying to be greater than or equal to 0 based on our symbol in the problem, we are going to be using a closed circle for that critical value. Now the next step is to determine the values that make the denominator equal to 0. Well, the value that would make my denominator equal to 0 would be if x were equal to 1. And that, it says right there, must be an open dot. And it must be an open dot because we cannot include any value in our solution that's going to make our denominator 0. So now I'm ready to think about my graph and think about my regions and test some values around my critical values. So I'm going to go ahead and I'm going to plot my negative 2 and my positive 1. Those are my critical values. I know I'm going to have a closed dot on negative 2, and I know I'm going to have an open dot on positive 1, and I'm going to be testing the values that I choose in the inequality 3 times x plus 2 over 1 minus x, and I'm looking for values that are greater than or equal to 0, which means that I want positive regions. Okay. So I need to test something that is less than negative 2. How about if we do x equals negative 3? I need to test something between negative 2 and positive 1. How about x equals 0? And I need to test something bigger than x equals 1. So how about x equals 2? All right, so now I have a quotient over here. So keep in mind that when I do my calculations, I'm going to be thinking about that. So in my numerator, I've got that positive 3, and then inside the parentheses when I plug in negative 3, that's going to make my numerator negative. In the denominator when I plug in negative 3, that's going to make 1 minus negative 3. That's going to make that positive. Negative divided by positive is going to give me a negative for that region. I don't want that region. I want positive regions. Let's try x equals 0. When I plug 0 in, 0 plus 2 is going to be 2. 2 times 3 is going to be 6, so that's going to make my numerator positive. In my denominator, when I plug in 0, 1 minus 0 is positive 1. Positive divided by positive gives me positive. So that region right there is going to be part of my solution. And then I have to check my third region where x is 2. When I plug in 2, 2 plus 2 would be 4 times 3 would be positive 12 on the top. So I have a positive value upstairs. And 1 minus 2 would give me a negative value downstairs, which leaves me with my last region being negative. So it looks like my solution is going to lie between negative 2 and positive 1. Okay, so then my answer, if I wrote it in interval form, would include negative 2, so it's going to be a closed bracket, comma, positive 1 with a round bracket on the 1. Okay, and again, my graph is right there. Now we're going to change gears a little bit and we're going to start talking about absolute value inequalities. Remember, absolute value by definition is the distance a number is from 0 on a number line. So if we see the inequality, the absolute value of x is less than c, okay, well, that means we've got x is less than c and x is greater than negative c, which ultimately we could write as a sandwich and say negative c is less than x, which is less than positive c. There we go. Okay. On a graph, these would be open circles because we've got less than symbols, not less than or equal to, and our shading here would be between those two values. If we change our symbol to less than or equal to, the only thing that's going to change is our open circles become closed circles. So we're going to have x is less than or equal to c, and x is greater than or equal to negative c, which means we can sandwich our x in the middle into negative c is less than or equal to x is less than or equal to c, and we're going to have closed circles around our c and negative c with our shading in between. The hint to help you remember less than or equal to and less than are and statements. It's a little rhyme here. Less than is and. And a graph of an and statement is always sandwiched between the two values. So you can see the word and is in the word sandwiched. All right, now let's flip our symbol around. The absolute value of x is greater than c. So that either means x is greater than c or x is less than negative c. There's no way to write an or statement as a sandwich. You have to write it as two separate pieces. So these are going to be open circles, and ors always shade on the ends. So our graph's going to look like that. The absolute value of x is greater than or equal to c. Again, we're just changing those circles from open to closed and changing our symbols and our inequalities. So now these are going to be closed circles, but it's still an or statement. So our shading is still going to be on the ends. The hint to help you remember is greater is or. And the graph of an or statement looks like the oars in a boat. See that word or there? The oars in a boat. So let's use this knowledge to solve a couple of absolute value inequalities. Okay, we want to express our answer in interval notation, and we want to graph our solution set. Okay, remember that we want to write these as either an and or an or statement depending on what we have. Less than is and, greater is or. So when we look at number 1, we have the absolute value of x plus 7 is greater than 6. So greater is or. This means that we are either going to have x plus 7 is greater than 6, or we are going to have x plus 7 is less than negative 6. Now we just have to do the algebra. So we solve for x on both sides. On the left side, we get x is greater than negative 1. On the right side, we get x is less than negative 13. Graphically, negative 13 would go on the left on a number line, and negative 1 would go on the right. Remember, smaller numbers on the left, bigger numbers on the right. Based on our symbol, these are going to be open circles. Ors always shade on the ends. Okay, so this would have to be a union of two intervals. So if we were going to write this in interval notation, our solution would be negative infinity, comma, negative 13, union, negative 1, comma, infinity. Number 2, there's a little bit of a trick here. We're going to make a little note. On this problem, we have to isolate the absolute value expression before splitting it apart. Okay, isolate the absolute value expression before splitting it apart. So that means that first we have to add 5 to both sides because we have to get that absolute value of 2x alone. So that gives us 2x is less than or equal to 15. Now we can split it. Less than is and. So we are going to have 2x is less than or equal to 15 and 2x is greater than or equal to negative 15. In both cases, all we have to do here is divide by 2. So we end up with x is less than or equal to 7.5 and x is greater than or equal to negative 7.5. So on a number line, negative 7.5 goes on the left and positive 7.5 goes on the right. These are closed circles, and our shading is going to be between them. Now we could write our answer as a sandwich. Okay, we could totally write this as negative 7.5 is less than or equal to x, which is less than or equal to positive 7.5. And we can also express this in interval notation. It would be square brackets, negative 7.5, comma, positive 7.5, with solutions in between.